7.5 inverse circular functions. We're talking about inverses today. And you will want a calculator at some point, but real quick, here's some things we need to know. In a one-to-one function, each x value corresponds to only one y value, and each y value corresponds to only one x value. So one-to-one function is something that's kind of new to you probably. Back in Algebra 1, we talked about the vertical line test, and you probably remember that. Vertical line test is not the same thing as one-to-one function. When we did the vertical line test, we were just trying to show that it was a function, okay? And every x value corresponded to one y value. And what that meant was, if I give you a function and you plug in 4 and get 17, and then you plug in 4 and get 25, that's a huge problem. That can't possibly happen. And so without doing any math, that's kind of what this shows. Each x value corresponded to this one y value, or this one, as opposed to if it hit twice. When we had a sideways parabola, and you're like, well, if I plug in 4, I get 17, but if this person plugs in 4, they get 25, that's a problem. That was not a function. Okay, so one-to-one is kind of the same concept, but instead of the vertical line test, it's the horizontal line test. All right, so we're looking to see if it only crosses one time on the horizontal line test. If a function f is one-to-one, then it has an inverse. And so this is the concept that's kind of important. And if this doesn't happen, then we can't even talk about an inverse. If we don't have one-to-one-ness, then we can't talk about an inverse. I think that's a really tricky thing to think about. The domain of f is the range of f inverse, and the range of f is the domain of f inverse. All that says is we're going to switch x and y, and that might be familiar to you because I know we must have talked about that earlier. I know you would have talked about that in algebra class when you found an inverse. The graphs of f and f inverse are reflections of each other across the line y equals x. And then last, here are some steps on how to find an inverse. First thing we're going to do, replace f of x with y and switch x and y. Number 2, isolate y. Number 3, replace y with f inverse of x. Okay, so that's just kind of some basic things. Let's actually find an inverse. This, you should remember problems like this from some other class, but we're going to call that y. And we're going to switch x and y. That's step 1. Step 2, we're going to isolate y. And you can do some of this in your head, I think. Subtract 4 over. If I want to get rid of that cubed, I'm going to do a cube root. Now, I'm going to do something real quick. I'm going to write the y on the left side. Just kind of interchange sides. Y is going to equal the cube root of x minus 4. Last step, we would just change that y back to function notation. F inverse of x equals the cube root of x minus 4. That's the inverse. What an inverse is it's going to cancel out the function. When we think of inverse operations, if I say times 5, you say divide by 5. If I say plus 4, you say minus 4. Inverse operations are what kind of cancels all the numbers out. In order to have an inverse, f of x must be a one-to-one function, meaning each range element is used only once. An easy test for this is the horizontal line test. As opposed to the vertical line test that you've seen before. So again, if you go back to algebra class, looks something like this, a parabola. It passed the vertical line test, so it was a function, but it's not one-to-one. The one I just had you do a second ago when you found an inverse was a cubic. A cubic is what I call a disco function. And if you think about a cubic, it is one-to-one. And we need it to be one-to-one in order to even talk about having an inverse. But here we have a problem. Okay, if you look at the graphs of all of our trig functions, all 6 of them, there's not one of them that's going to pass that horizontal line test. All right, so we're not technically even allowed to talk about an inverse because they're not one-to-one. They're not going to pass that horizontal line test. So we must restrict the domain. We have to do something kind of weird. We have to pull a rabbit out of our hat and do some sort of magic trick to be able to do this. All right, so check this out. What you see on the screen in red is the sine curve, y equals sine of x. And I've got a green horizontal line showing that that sine curve does not pass the horizontal line test. All right, this is not one-to-one, so I'm not technically allowed to talk about an inverse unless you restrict the domain. And so look up here, I've got some flashing colors there. If you look at the green or the purple or the orange, if you only look inside those colors, one of those regions would actually be one-to-one. Which color looks like it would actually be one-to-one? Purple? I don't know. Purple hits twice. Orange, the green only intersects the red one time. So the answer to that question, it's going to be one-to-one in the orange region. Okay, so if you look at the orange region, look at where I restricted it down here in orange on your equations. It goes from negative pi over 2 to positive pi over 2. I'm going to want to restrict my equation to only look between negative pi over 2 and positive pi over 2. So when we get to this table looks like a big jumbled mess, all right? But what you would notice is that when I do an inverse sine function, this right here is my restriction. It's my range. My range is from negative pi over 2 to positive pi over 2, which is kind of a weird thing, okay? So what if we look at a cosine curve? All right, this blue is a cosine. So again, same thing. We've got to restrict it. And so you're looking at green, you're looking at purple, you're looking at orange. Only one of those is going to actually be one-to-one because only one of those, the green, is going to intersect the blue one time, not two. Do you see which color it is this time? This time it's purple. See that purple? Green intersects blue one time, and so I look over here at my equations, I look at purple. Purple is from 0 to pi. From 0 to pi, and this is really weird, okay? But I'm looking right here. It's restricted from 0 to pi. This is really important, and this is necessary because without this extra little thing, it's not one-to-one. And we can't really talk about an inverse. So let's look at one more. Let's look at a tangent function. Okay? So again, you've got a tangent curve in black, and we're looking at green, we're looking at purple, we're looking at orange. Purple looks like it could maybe work. It's kind of confusing to look at purple. I think it's much better to look at orange here in this case. Orange, it only hits one time. That's one-to-one. If I only look at the orange part, that's one-to-one. And again, your orange was the region between negative pi over 2 and positive pi over 2. And so I'm literally looking at an inverse tangent. I'm looking right here. It's almost the same as the inverse sine. The difference is the parentheses mean we don't want to include those boundary lines, and that's because of the asymptotes in the graph. Remember graphing a tangent function last chapter, we had all these asymptotes. So it's the same, but it's not quite the same, okay? Now, what's really weird and probably more useful is we want to be concerned about the quadrants over here, okay? So notice, where are we at here? If I look at inverse sine, it's defined from negative pi over 2 to positive pi over 2. So think about this. Negative pi over 2 is like going backwards this much. Positive pi over 2 is going forward this much. And so what this interval says is I only want answers, it's the range after all, it's the output, between negative pi over 2 and positive pi over 2, like this. Okay? It is only defined in quadrants 1 and 4. And this is going to be really weird for you because all semester long we've used the chart and we've done sine problems and we've always said, well, sine is going to be negative in the third and fourth quadrants. Think about how many times we've said that. There's no such thing as the third and fourth quadrant, or the second and third quadrant, though. This problem literally doesn't have a second or third quadrant. There's no such thing, okay? Why? Because of this picture. I had to restrict the domain to even make it work. If I don't restrict the domain to just that orange region, it's not going to be one-to-one and it's not going to have an inverse and I'm not going to be able to talk about it, okay? So I have to restrict it in this way. It's only defined in the first and the fourth. So that kind of makes it easier though, because if you get a positive number, you know you're talking about the first, and if you get a negative, you know you're talking about the fourth. Now, if I look at the inverse cosine function, I know it's only defined from 0 to pi, or the first and second quadrant. There's no such thing as 3 and 4, and it's really weird for us to think about that, but there's no such thing as 3 and 4. I know that if I'm talking about a positive value, it's in the first, and a negative value, it's in the second. So you gotta go back and look at this chart over and over and over again, constantly, constantly, constantly. Okay? So let's try some examples here. I'm gonna pull up my chart. When I say arc sine 1/2, it's the same thing as doing inverse sine. And so you should be able to look at the chart and say, okay, here, 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 5 or 6. Okay, you should use the chart the same way we always have been using the chart. Inverse sine of 1/2 is going to have something to do with pi over 6. Okay, but what you have to do every single time, and you're going to have to force yourself to do this, is to think about where it's defined. So you look at the range, and you say, well, the range for an inverse sine is negative pi over 2 to positive pi over 2. Or in other words, you're saying it's defined in quadrants 1 and 2. But this is a positive number. And my positive number tells me that I must be in quadrant 1. If you sketch this out, you've just got a pi over 6 angle in quadrant 1. And so honestly, there wasn't really much to do because we're in quadrant 1. It is what it is, and that's my answer. Question? Yes, I did mean quadrants 1 and 4. Thank you very much. Shoot. 1 and 4. Thank you very much. That was a big mistake. I would have got that right even though I made a mistake, because quadrant 1 is my positive and that's what I'm looking at. And one thing that's good, I guess, about this is every time we're talking about a positive, it's going to be in quadrant 1. When it's negative, it's either going to be 2 or 4. So I look at this next one, inverse sine of negative 1. So again, I'm going, okay, over here, I'm looking at this. This is pi over 2, but specifically it's pi over 2 where inverse sine is negative, okay? And I know inverse sine is negative in the fourth quadrant, all right? So I've got the same exact range, but this time I'm looking in the fourth quadrant. And so if you look at this drawing, we have to go like this, negative pi over 2. Now, one thing that's tricky is we've done a similar thing to this, a similar angle to this all semester long, and we've said, okay, if this is 0, and this is pi over 2, and this is pi, and we called this 3 pi over 2. right? And we went around here and we called this angle 3 pi over 2, but that's not right. That's out of bounds. If you want to look at it on a calculator, you're going to say, okay, pi over 2 is 1.57. So essentially what this says is you've got to give me a number between negative 1.57 and positive 1.57. That's going to be my answer. And so if you tried 3 pi over 2, oh, that's out of bounds. 4.7 is out of bounds. You have to have a number between negative 1.57 and positive 1.57. That's not going to work. So here's what I would ask myself. All right, listen very carefully here. When I see this range right here, I would ask myself, am I allowed to have a negative answer? If I'm allowed to have a negative answer, then the answer, I just stick a negative. Negative pi over 2. That's my answer. Okay? Last chapter and the one before, we weren't really talking about a negative because we had to be between 0 and 2 pi. This time, I can have a negative. All right, next one. Inverse sine of negative 2. You might be confused because that's not in the chart, but it doesn't have to be. All right? You look back at this, and I didn't really mention the domain. We talk about domain, and I don't want you to think of domain as the x numbers. I want you to think of domain as input values and range as output values. Okay? The domain is what you're allowed to plug in. And when we're looking at an inverse sine, what this says is I'm allowed to plug in anything between negative 1 and 1. I'm allowed to plug in anything between negative 1 and 1. If you look, well, never mind. So when I see this problem, am I even allowed to plug in negative 2? I'm not. So this is undefined. Undefined. Okay, so good news. If you know what you're doing, these problems are really fast. Inverse cosine of 1, 0. Oops, we're in radians. 0. And so I don't really need to think about my range at all. The range for inverse cosine is from 0 to pi. This one is defined in 1 and 2 for sure. Positive in the first quadrant, negatives are in the second quadrant, but 0 is neither positive nor negative. I don't really have anything to think about. That's the answer, 0. I think part B is a lot more interesting. Inverse cosine of negative square root of 2 over 2. So you're looking here, you're looking here, you're looking here. It's pi over 4, where inverse cosine is negative. And so here's where you're going to mess up. Some of you are just going to stick a negative on here. All right, but what you have to ask yourself is, am I allowed to have a negative answer? And that answer is no, you're not allowed to have a negative answer. Your answer has to be between 0 and 3.14. You better not give me a negative number here, because your answer has to be between 0 and pi. And so you have to think about it as, okay, this means we're defined in these two quadrants. So if you look at it, what we've got is a pi over 4 angle in the second quadrant. The negative doesn't mean that your answer is negative. Your negative is telling you where to look. Inverse cosine is negative in the second quadrant. So we draw that angle in the second quadrant, and we say, okay, what angle is this? And so you do that the same way we've done before. We know halfway is pi right there. We get a common denominator, so call this 4 pi over 4. And so this is right before 4, it must be 3. This answer is 3 pi over 4. And sure enough, if you did 3 pi over 4, you get about 2.36. You're getting a number that's in between 0 and pi, in between 0 and 3.14. So that checks out. That works. Notice the next one is in degrees. So we're saying, okay, inverse tangent of 1. All right, now remember, on my chart on the board, you don't see this bottom row, so you'd have to understand that to get the 1, you're dividing those two. But we're finding the angle, and so in degrees, we're looking at a 45. If there's no negative, it just is what it is. We don't really have to think about this at all. All right, inverse tangent is defined from negative pi over 2 to positive pi over 2, or since we're in degrees, we can say from negative 90 to positive 90. But we know it's defined in quadrants 1 and 4. This positive value right here just tells me to look in the first quadrant. It is 45, and that's all I'd have to do there. So then the next one, inverse secant of 2. You might be thinking, well, we're not allowed to plug in 2, but look back at secant. If you look back at secant, or inverse secant rather, inverse secant has this as its domain. And that says I'm allowed to plug in anything from negative infinity to negative 1 or positive 1 to infinity. So 2 is going to fit in here somewhere. I'm allowed to plug in 2. I'm allowed to. So this is not undefined. I'm allowed to do this, but you still don't know how to do it because of the way the chart is written. If you had a bigger chart, this would be easier. Here's what I would do. Okay. I'm not going to play with secant. I'm going to say I know that secant is the reciprocal of cosine. So we're going to change this into inverse cosine of 1/2. Reciprocal, reciprocal. Inverse cosine of 1/2 is going to be a lot easier to deal with. Because I'm going here, and we're in degrees, so I go to 60 degrees. I don't have any negatives, so I don't have to think about any kind of extra thing. I know this positive result tells me we're in quadrant 1. Has to be. Number 4. Find y in radians if y equals inverse cosecant negative 3. So really, same thing. This one says use a calculator. I guess that's different. But I don't know how to do cosecant, so I know the reciprocal of cosecant is sine. I'm going to do inverse sine of 1 over negative 3. Okay, I'm using a calculator. Better make sure you're in radians, because that's what it says. Better make sure you're in radians. Radians, inverse sine 1 over negative 3. And I get that. Okay, negative 0.3398. Calculator questions are kind of tricky sometimes. It's strange and you're not going to believe it, but sometimes your calculator doesn't give you the right answer. You really, really have to think about what your calculator is telling you because sometimes it's not right. You're going to have to think about the domain and the range. All right, the range of cosecant. Keep in mind, this is a cosecant problem, not a sine problem. This is inverse cosecant. So 1, 2, 3, 4. The range is negative pi over 2 to positive pi over 2, not equal to 0. What I would ask myself here, you don't need to write it down, you just need to look at that on a chart. I would ask myself, am I allowed to have a negative answer? Okay, and this says I am. And so that means that is the answer. Sometimes you won't be allowed to have a negative answer. Sometimes you will. You really, really have to pay attention to that chart and those ranges. Okay. So the next one says we're in degrees and we're going to do the same thing. So I don't know inverse cotangent, so let's do the reciprocal and change this to tangent. Inverse tangent of 1 over negative 0.3241. So we're definitely in degrees. Let's switch it to degrees. We're doing inverse tangent 1 over negative 0.3241. and I get negative 72.04. Negative 72.04 degrees. Okay. But we have to go back and look at the range. Okay. You're constantly saying, is this possible? Inverse cotangent. Inverse cotangent is right here. I'm looking at this range, 0 to pi. Inverse cotangent is a 0 to pi. Or I guess, since we're in degrees, we can say 0 to 180. But the question is, am I even allowed to have a negative answer? This range is talking about your outputs, and this range is telling me I'm not allowed to have a negative answer. So you better not tell me negative 72. If I tell you I need a number between 0 and 180 and you tell me negative 72, you got to know that's wrong. Okay? 0 to 180 tells me that this is defined in quadrants 1 and 2. So what you would do is you would say, well, there's only 1 and 2. There is no 3 and 4. This negative isn't really a negative. This negative is telling me I got to be in quadrant 2. So what I've really got is a 72.04 angle in the quadrant that makes it negative. So then we're going to say, all right, so what's that angle? And all that you have to do here is say, well, halfway around is 180. Let's just subtract. 180 minus 72.04. It's 107.96 degrees. And that's super tricky because that is not what the calculator said. All right. The calculator did not tell us the right answer there. You've got to be smart enough to think about where it is and what that means. It's always what and where. Calculator did a good job of telling me what. It did not do a good job of telling me where. It just kind of hinted at it. All right. Now, this kind of problem without a calculator, I really like this kind of problem. All right. But you have to understand one thing really well. When you're finding an inverse trig function like this right here, when you're finding an inverse trig function, you are finding an angle. So go ahead and make that markup on your paper. Circle that inverse tangent 3 over 2 and put a little theta right there. You want to understand really well that that is an angle. And it's tricky because we've done trig functions all semester long, but when we were doing sine and cosine, we were talking about the sides. X over R or Y over R, we were talking about the sides of that triangle. When we're doing an inverse, we're talking about the angle, okay? We're going back and forth between the two, but this is an angle. And so I'm going to draw a picture of this angle, okay? Now, when we do an inverse tangent, we know inverse tangent has a range from here to here. And that's telling me that it's defined in quadrants 1 and 4. Because this 3/2 is a positive number, it's got to be in the positive quadrant. I know my angle is in quadrant 1. All right, I know my angle is in quadrant 1, so I'm going to draw a picture in quadrant 1. We've got some angle theta in quadrant 1, but what we really care about is this triangle formed. Now, the 3 over 2 has to do something with a tangent function, right? And we know tangent is talking about y over x. It always has been ever since the first day of class. We're talking about y over x. And so in my triangle, I can say the y number and the x number. And I can find the missing side the way I always have. Now, I would highly recommend you to figure out how to do Pythagorean theorem in your head. 2 squared is 4, 3 squared is 9, add them, that's 13. It's going to be square root of 13. Okay, if you can do this part in your head, then you're going to have an advantage because it'll be faster. If you can't do that in your head, you're going to have to come over here and do Pythagorean. 2 squared plus 3 squared equals r squared. That's 4 plus 9 is 13. When I solve this, normally it would be plus or minus, but we understand that this r is a radius of a circle and it will never be negative. X and y can be negative, r cannot. So I got that square root of 13 right there. I've got my three sides. Now, last step is to understand that you're just taking sine of that angle. We want sine of that angle. We want the sine ratio of that angle. So if you look at the triangle, we know sine is y over r. And we got to clean that up. But that's basically the answer. We're going to rationalize in the usual way. And we're going to get 3 square root of 13 over 13. There's your answer. I like those problems. Sine theta is equal to that. Yes. Okay. Or actually this. Because technically there was no theta in the problem, but yes. So all of these problems are kind of the same thing. That's one reason I like them. You figure one out, and then you can do every single one of them. But the key for me, I think I had a hard time until I really, really thought hard about what this was. That is an inverse trig function, and an inverse trig function is an angle. So I'm going to draw a picture of that angle. The trick is you got to tell me what quadrant it's in. Okay? So we know it's an inverse cosine. Inverse cosine is 0 to pi, right? So you want to think about what quadrant would give me a negative value. 0 to pi is quadrants 1 and 2. This negative value is telling me make sure you put it in quadrant 2. Okay, negative quadrant 2. So I'm just going to draw a picture of my angle in quadrant 2. Angle theta puts me in quadrant 2, but again, I want this triangle. I notice sometimes people don't draw their triangle correctly. Remember that one side is a radius of a circle. If you draw your triangle like this, you can't make that line the radius of a circle. It doesn't make any sense. So don't draw your triangle like that. We've got the cosine ratio. We're talking about x over r. So I've got my x number and my r number. And maybe you've seen these numbers enough that you know that last number without having to do Pythagorean. Anybody know what the last one is? 12? 12. There's a 5, 12, 13 that comes up a lot. If you didn't know that, do your Pythagorean, find that that's 12. But once we get that, we have to just understand that we're finding tangent of that angle. Tangent of that angle, remember tangent is y over x, negative 12 fifths. Y over x, negative 12 fifths. As soon as you understand what are these problems, they go quickly. All right, so 6a. Looks pretty hard. Every time it says evaluate the expression without a calculator, it makes me think that it can be done with a calculator, and I'm not supposed to, but I suppose you could just type this in. That's kind of cheating though, right? So let's just not do that. Here's what you've got to do. I see an inverse trig function right here, so I know that's an angle. I'm going to mark this with an A. I see a different inverse trig function right here, so I'm going to mark it with a different letter B. And you don't have to use A and B. You just have to make sure you understand that's two different angles. You could do theta and beta if you want, X and Y if you want. Doesn't really matter. You get two different angles though. So make sure you understand that's two different angles. Okay? When I see this number right here is positive, square root of 3, automatically tells me it's quadrant 1. Okay? Every time it's positive, it's in quadrant 1. So I'm going to draw a picture of angle A in quadrant 1. All right? Now we've got the tangent ratio. I know it doesn't look like it, but square root of 3 we would think of as square root of 3 over 1. We want it to be a fraction so we can get that ratio. We know tangent is y over x. So I've got these two sides right there, y and x. Now maybe you can do the Pythagorean in your head and find that missing side. If not, you're like 1 squared plus square root of 3 squared equals r squared. That's 1 plus 3 is 4. Square root gives me 2. That side's 2. Okay. Now hang on, because you can't do anything with that just now. So hang on to that for a second. I've got this other angle, B, and I notice this one's also positive. So this one is also in the first quadrant. This is quadrant 1. This one was in quadrant 1. So I draw another picture in quadrant 1 of angle B. Can't use the same picture. You gotta use a different picture. It's two different angles. We've got the sine ratio. Sine is y over r, like that. So if you do Pythagorean in your head, it's going to be 9 minus 1 is 8. It's going to be square root of 8. It's going to be square root of 8 right there. If you couldn't do that in your head, then by all means, go over to the side, do Pythagorean theorem. That's square root of 8. Square root of 8 reduces to 2 times the square root of 2. You can do that at some point as well. Now, what you have to realize is you're finding cosine of angle A plus angle B. Where have you seen that before? That's one of our identities, right? On the board, it's number 4A, right? It's number 4A. And so this identity, find it on your formula sheet, but this is going to be cosine minus sine. And I've got to fill in the blanks. I've got cosine minus sine. Well, cosine A, look back at your triangle. Cosine is x over r. X over r, so cosine A is 1/2. Cosine B, x over r. That's square root of 8 over 3. Sine of A is y over r. That's square root of 3 over 2. And sine of angle B is 1 over 3. Use your picture to fill in those blanks. Now let's just clean up our fractions. Multiply these, you get square root of 8 over 6. Multiply these, you get square root of 3 over 6. I would combine those into a single fraction. Square root of 8 minus square root of 3 over 6. And I would probably give you that, but technically you should probably reduce. Square root of 8 turns into this. So this is probably a better answer. It's more reduced, but I would give you either one of them. Example 6b, we're going to evaluate the expression without a calculator. I think it's insanely important that you understand that an inverse trig function is an angle. So go ahead and do that. Circle that inverse trig part and call it angle theta or whatever you want to call it. It doesn't have to be theta. All right. Do not circle the 2 in the front because that's not part of my inverse trig function. Inverse trig function is an angle. Now, we're talking about inverse sine, and we know inverse sine is defined from negative pi over 2 to positive pi over 2. Or another way of saying that is it's defined in quadrants 1 and 4. So when I see this 2/5 is positive, as soon as I see those numbers are positive, 2/5 right there, I know we have to be in quadrant 1. This angle that they're describing has to be in quadrant 1. And so I'm going to draw a picture of this angle that they're describing in quadrant 1. Theta is an angle in quadrant 1. But what I'm really after is this triangle. That angle defines a right triangle. And what I have given to me, what I've circled, is basically the sine ratio 2/5. I know I'm talking about a sine ratio, so I know I'm talking about y over r. I've got two of the sides of this right triangle. I've got the y side and the r side. You should probably be good enough at Pythagorean theorem to be able to do that in your head now and figure out that missing side. Okay, if you can't, you can always do Pythagorean, but I'd love for you to be able to do this in your head. Subtract over, square root. You'd have plus or minus square root of 21, but we're in the first quadrant, so we know it's got to be the positive version. Square root of 21, right there. Okay? So once you get that filled out, you probably have everything you need, but then you need to realize that we're taking tangent of twice that angle. So rewrite, you've got tangent 2 times that angle. And so it's not as easy as just doing the tangent ratio. We can see tangent theta is y over x, but we're not asked to find tangent theta. We're asked to find tangent of twice that angle. It's a completely different angle, different picture, okay? But what I do is I recognize that this is one of my identities. Tangent 2 theta, I've got a double angle identity. And if you look at your formula sheet and find it, or you look at my board and find it, on my board it's labeled number 5e. Tangent 2 theta is 2 tangent theta over 1 minus tangent squared theta. Like that. Okay. So I'm going to use my picture. I'm going to use that tangent theta within this identity. It's kind of a mess from this point because you've got some weird, messy fractions. I'm going to plug in tangent right here and here. So we've got equals 2 times that tangent theta was 2 over square root of 21 over 1 minus, and again, tangent theta was 2 over square root of 21, but then we have to square it. So I've got a bunch of stuff that I'm going to need to clean up here. On the top of my fraction, keep in mind that's 2 over 1, so you can multiply your fractions on the top here. That's 4 over the square root of 21. That's the easy part. On the bottom, you've got 1 minus, and then you need to square that fraction. That's going to be 4 over 21. Okay. Lots of stuff going on here. Mainly, we're just trying to clean up fractions at this point. Okay. This fraction bar implies parentheses. We're going to have to combine those fractions there. We're going to have to subtract those things first. So we know when we subtract fractions, we get a common denominator. So I'm going to call that 21 over 21. And so I can subtract. I'll have the 4 over square root of 21 on the top, but on the bottom, 21 minus 4 is 17. I've got 17 over 21 here. Now, notice one of those is a square root and one of those is not. You can't just knock out those 21s because one of them is a square root of 21 and one of them's a 21. They're not going to cancel out. We are dividing fractions. So in order to divide fractions, we're going to multiply by the reciprocal. And we multiply by the reciprocal, but I'm gonna cheat and save a step here. I also see I'm gonna have to rationalize. I know I'm gonna have to rationalize. So let's multiply by square root of 21 over square root of 21. A lot going on here. Okay. Now you could say 4 times 21 is 84, but I'm not going to just yet. 4 times 21 times square root of 21 on the top. And on the bottom, when you do a square root of 21 times a square root of 21, that is 21. times the 17. The reason I did that is because it makes it clearer that those 21s are going to cancel out. So 21s cancel out, and you're going to end up with 4 times the square root of 21 over 17. Those fractions are messy and gross, okay? I don't think the trig part is the hard part. I think the algebra part is definitely the hard part of that question. But kind of go back and look at the main recipe for this problem. Recognize that that inverse trig function, the inverse trig is an angle. So try to draw that angle. And then we used that tangent 2 theta. So we used an identity and our picture. And then we just had to clean up a whole bunch of fractions. Questions on that? Okay. Next one's weird because there's a u. It's not numbers. It's a variable. But we're going to try to do the same thing. I look at this. I see an inverse tangent, so I know that's an angle. I know inverse tangent is defined in quadrants 1 and 4. So the tricky part for me is because I don't know what u is a variable. U might be positive and it might be negative. So technically we don't know which quadrant it's in at this point. And you know, you could draw it in either one really. So I'm just going to draw, it turns out it's the same either way. I'm just going to draw quadrant 1 because it's easier. Okay. So I've got an angle theta in quadrant 1. But what I'm really after is this triangle. Since I've got tangent, I know I have the tangent ratio y over x. So that ratio, we're going to call u over 1. I know they don't give you a fraction, but you technically want it to be a fraction because you need 2 of the sides. You've got the y side and the x side, u over 1. And so once you've seen these a few times, you're going to be able to do Pythagorean on this one in your head, but maybe you're not there yet. So you go u squared plus 1 squared equals r squared. And that's just u squared plus 1. Square root both sides to isolate. You're going to get r equals, plus or minus square root of u squared plus 1. But it's an r, so it's always going to be the positive version. And so this hypotenuse here is the square root of u squared plus 1. Now, I always have some people try to clean this up, and they try to say that the square root of u squared is u, and the square root of 1 is 1, and so they say u plus 1. But that's not how it works. Okay, that's not how it works because of order of operations. It always helps me to put in some numbers. If I said the square root of 25, oops, not that. Let's say the square root of 5 squared plus 1. I would expect everyone in here to know that that's going to be the square root of 26 because you cleaned up all that stuff inside first. And then, whatever that is, 5 point something. But if you're trying to do this trick, you're going to say that's 5 plus 1 is 6, and that's clearly not true. All right, that can't work. It has to do with the order of operations. Do not do that mistake right there. All right. The square root implies there are parentheses there. You'd have to do that before the square root. Anyway, long story short, we just found the radius of the circle is square root of u squared plus 1. Why that's important is because we're trying to find the sine ratio of that angle. And sine of that angle, we know sine of that angle, we're talking about y over r. So in this problem, the y value is u. The r value is the square root of u squared plus 1. As soon as we rationalize that, we'll have the answer. So rationalize in the usual way, we're going to multiply by, the square root over the square root, right? And so we're going to get something crazy. U times the square root of u squared plus 1 over u squared plus 1. (7b), write cosine of 2 inverse sine of u as an algebraic expression in U. So we can do the same thing. If we recognize that this inverse trig function is an angle, I'm going to do the exact same thing. I know inverse sine is defined in quadrants 1 and 4. Technically, I don't know which one it is because I don't know the value of U, but it's going to work out the same either way. So just draw it in quadrant 1. You've got this theta angle that defines this right triangle. Since we've got the sine ratio, we've got y over r. So y and r, u and 1. We need to find that missing side. We can do Pythagoreans again. U squared plus, x squared plus u squared equals 1 squared. Subtract this over, x squared equals 1 minus u squared. Notice I went ahead and did the square. 1 squared is 1. Square root both sides. You're going to have plus or minus square root 1 minus u squared. Now remember, x can be negative. R could not have been, but x can be negative. But since we drew this over here in the first quadrant, we know that's going to be the positive value. Square root 1 minus u squared. So once you've got your picture drawn, you come back and you say, well, look, we're finding the double angle cosine. The double angle cosine. In double angle cosine, you look at your identities, you've got 3 different choices. On my board, I've got them labeled 5B, C, and D. Honestly, though, even though you've got 3 choices, I think I'm going to stay away from one that deals with the x coordinate just because it looks more complicated. I'm not going to pick one with a cosine in it because for a cosine, I'd have to deal with that. And it's not a big deal. I can deal with it, but I think it's going to be a lot easier if I do one with a sine in it with the y coordinate. Okay, so I'm picking the one that says 1 minus 2 sine squared theta. Doesn't really matter. I just feel like that's going to be easiest. 1 minus 2 sine squared theta. So I can see from my picture that sine theta is u, right? Sine theta is u over 1, u. So I've got 1 minus 2 times u squared, or 1 minus 2 u squared.